Picture this. 9 out of 10 students walk into their computer science exam, write down an answer that feels totally logical, and just quietly lose an entire grade boundary. I mean, it's brutal. They don't fail because they didn't study. They fail because they fall right into these predictable, hidden traps set up by the phrasing of the exam itself. So in this explainer, we're not just memorizing the syllabus. We're going to literally hack the mark scheme. Let's expose the exact mistakes people make before you even step foot in the exam hall.
Right off the bat, look at this tiny snippet of broken pseudocode. Seems innocent enough, right? But this right here? Absolute grade killer. We've got a failed initialization slapped together with a completely backwards boundary logic error. Like assigning 0 to the total when it actually might need to track a running sum. And oh man, using a less than operator instead of greater than or equal to for an A grade. When you're in those final 20 minutes of the exam and the panic kind of sets in, your brain just breezes right past these microscopic logic flaws.
Okay, let's dive into exactly where that logic completely falls apart. You absolutely have to separate the mechanism of assignment from selection in your head. Assignment, which is what you're seeing symbolized by the box, is literally just storing a value in a variable. That's the whole shebang. Selection, mapped out over in the flowchart, is basically the electronic equivalent of human decision-making based on some really strict criteria. The computer uses those criteria to take different paths through the code. When you mix those two up or mess up the operators, boom, your code breaks. Examiners know this, which is exactly why they specifically test your ability to spot improper variable scopes and syntax errors.
And hey, it's not just the programming logic where students stumble. It's how they actually explain it. Check out the generic textbook answer. An algorithm is a set of instructions. Is it safe? Maybe. Is it earning top marks? No way. The top band answer upgrades this massively by taking the exact technical definition and applying it to the specific nouns in the scenario. Like, an algorithm for the ticket system includes an if statement to check if age equals 18. That is what examiners reward. They don't want floating dictionary definitions, you know? They want applied logic.
All right, moving on to mastering denary to hexadecimal conversions.
So you're sitting there, the clock is ticking, and you have to convert a denary number to hexadecimal. The single biggest trap here? Trying to do it all in your head. Seriously, if you do that and make one tiny little arithmetic slip, you lose every single partial mark available. It's just not worth it. The fix is what we call the binary bridge method. Think of this as your Rosetta Stone for the exam. Hexadecimal is basically just a human-friendly shorthand for binary, right? Each hex digit represents exactly 4 bits, or 1 nibble. By forcing yourself to physically write out that intermediate binary step, you build a literal bridge between base 10 and base 16. That way, even if your final hex calculation is a little bit off, the examiner sees your thought process and you still get those partial marks.
Let's quickly break down the exact 3 steps to lock in those points. Step 1. Convert your base 10 denary number into an 8-bit binary byte using the standard place values, 128, 64, 32, and so on. Step 2. Take that 8-bit string and slice it right down the middle so you get 2 4-bit nibbles. Step 3. Map each of those nibbles independently to its corresponding hex character. If you faithfully followed this exact sequence on your paper, the conversion literally becomes foolproof.
But honestly, why do we even care about hex? Well, because the exam won't just ask you to do the math. They're going to ask for the application. You have to anchor this theory into the real world. The 3 most common, highly testable uses of hexadecimal are MAC addresses on network interfaces, HTML color codes in web design, and the formatting of IPv6 addresses. Just memorize this list. When the exam command word says identify a use case, this is your go-to ammunition.
Next up, let's talk about serial versus parallel data.
Now, a massive, and I mean massive pitfall for students here is writing super vague, non-specific responses when asked to evaluate data transmission. If you just write, "it's faster," or "it's better," you're getting 0 marks. You have to be hyper-specific and focus on the actual physical hardware differences. Just look at how the data streams flow here. Serial data transmission is literally a single bit moving down a single wire, one at a time. It's super organized, sequential, and highly reliable. But then you have parallel data transmission, which is firing multiple bits simultaneously across multiple wires. Sure, it sounds incredibly powerful, but as you can probably guess, keeping all those individual bits perfectly aligned over any real distance is a complete mechanical nightmare.
When you compare these side by side, the exam answers practically write themselves. Serial is absolutely your choice for long-distance communication, precisely because having just one single wire prevents data skew. Parallel, on the other hand, is strictly limited to short-distance internal computer connections. Think of a data bus inside the CPU, where you need to move a massive amount of data instantly, but you don't have to worry about long distances degrading the signal. So, the golden rule: always frame your answer around the strict requirements of distance and data flow.
All right, section 3, registers and avoiding what we call floating abstractions.
So one of the most painful things for an examiner to read is a floating abstraction. What's that? It's when you explain a concept absolutely perfectly in theory, but you score 0 marks because you utterly fail to apply it to the specific scenario in the question. You have to ground your technical knowledge in the exam's reality. A register isn't just some generic high-speed memory location. I mean, in a retail scenario, that register might be temporarily holding scanned barcode data before it's processed. Or in a banking scenario, it might be holding an encrypted PIN input. The key takeaway? You must tie the mechanical function of the hardware directly to the specific contextual nouns the examiner gives you in the prompt. To make sure you never write a floating abstraction, you can use this precise 4-step method when you're sweating under time pressure. Step 1. Identify the demand. Like, what is the question actually asking you to do? Step 2. Classify the concept. Are we talking about memory, transmission, security? Step 3. Sequence the steps. Explain the mechanism logically, moving from point A to point B. And finally, Step 4. Connect to context. Always relate your final output back to the specific scenario they gave you.
Let's actually see how that 4-step method radically transforms an answer about, say, internet structure. You can really see the leap here, from a totally safe, shallow description to a deep, mark-earning response. Look, if you just name a router, okay, you get a safe description. If you explain that a router forwards data packets between computer networks, great, you've got an explanation. But, and this is the kicker, if you apply it to a retail context, saying the router directs customer payment packets securely to the banking server, boom. You suddenly unlock full marks just through that level of specificity. And that brings us to our final section, the final exam strategy.
We've covered programming logic, number-based conversions, transmission hardware, and contextual application. But how do you actually tie all these totally distinct computer science modules together into one foolproof framework for exam day? Well, you build them into the 3-layer learning path. Notice how this progression stacks up. Layer 1 is simple language. You just have to grasp the real-world purpose first. Simple as that. Then, Layer 2 is technical vocabulary. This is where you replace your everyday words with precise subject-specific terms, like sample rate or bit depth. And finally, Layer 3 is the exam-style response. This is where you mold that technical idea into a tightly structured answer, designed specifically to satisfy the examiner's rubric while you're under intense time pressure.
And to perfectly execute that layer 3, you rely on this framework right here, CERW. Concept, evidence, reasoning, and wording. The absolute golden rule you have to remember is this: 1 mark equals 1 unique technical point. Actually, scratch that, let me be clearer. If a question is worth 3 marks and you write 1 beautiful technical point but you just repeat that exact same idea 3 times using different words, you are only going to score 1 mark. It's heartbreaking. You have to use the command word to identify the action, find the scenario nouns for your evidence, explain the how for your reasoning, and then lock the whole thing in with exact examiner wording.
If this structural breakdown made these concepts finally click into place for you, then you definitely need to subscribe to our YouTube channel, Ace the Exams, at the handle @acetheexams_IGCSE. We are constantly releasing deep dive explainers exactly like this one to help you totally crush your Cambridge examinations. We strip away all the fluff and give you exactly what you need to score those top marks. Sue, think about it. You've mastered the tricky logic of assignment, you can confidently bridge denary to hex without breaking a sweat, and you know exactly how to evaluate data transmission without falling into the vagueness trap. You are heavily armed for paper 1. But let me leave you with this one question. What happens when the examiner throws a massive multimedia file at you and asks you to calculate its compression without losing any critical data? Like, what hidden traps are lurking in your next paper when it comes to lossy versus lossless data compression? You're definitely going to want to find out before exam day. Keep analyzing, keep practicing, and I'll catch you in the next explainer.